All right, recorded is rolling. It is Friday, December 2nd. Yesterday, I went through some of these puzzles with you guys, the ones that I circled here. So I will do some more of those today. Uh, this coming week, I'm going to write a quiz for you guys. So we'll have an in-class quiz this coming Thursday. This will be open notes. So any notes that you guys take, you guys can use. Right. And then I'll start the midterm review with you guys next week. So let's switch screen here. Okay. I got some demos lined up for you guys. Run this. All right. Like I should have sold videos, but all right, so this one's from Steve Mold. This was just released a few days ago, but it's connected to some stuff we're talking about. So what happens when you put a billiard ball on a turntable? Now, most things you put on a turntable, they're just gonna like roll off, right? Like put like a coin or a race car. Yeah, let's get this thing going. Right, of course, just gonna like roll up, right? But why is a billiard ball not? Right? It actually, if you just get it in place, right, it'll just like stay there. Give it a little bump, starts like processing around. Right? So it goes to this whole explanation if you want to see this. But one of the connections to what we're doing is it brings up the rotational inertia of the ball. He counts how many times does the turntable rotate versus how many times does the ball revolve around at some point, say once he gave it a bump, start moving around, right? Hey, does this look familiar? Like you guys know I is equal to mr squared. And for a solid sphere, which this would be a billiard ball, right? You guys know that I is equal to 2/5 mr squared. You guys know that? Right? Now later on, he also puts something like a ping pong ball up there, which is like a shell, like spherical shell, which is like 2/3 mr squared. So the mr squared bit cancels out. You get some factor. And he's looking at why is there this relationship between like this turntable turnaround versus the billiard ball turning, right? So it comes out to this relationship. So yeah, if you want to check this out, see the full thing, it's on YouTube. Another thing I wanted to show you guys. Now this goes back a few years ago. This guy is Mark Rober. He used to work for NASA. He's got a YouTube channel now. He does a bunch of science and engineering things. Says, how can you maximize the chance of winning a Pinewood Derby race? So we've got these Pinewood Derby cars. I know like Scouts use them. You buy them a little kit. You have this wood body. You cut it, sand it down, paint it. You put on the wheels, right? And then they race these things. Right. So he goes through the physics principles of what would maximize your chance of winning, and also like breaks out some empirical science and figures like exactly like what factors would affect how much. Right, but I want to do a simplified version of this with you guys. So let me switch my screen over here, and let's get this up. So actually, let's go portrait with this. Okay. So say you got this is like the racetrack. Okay. We're gonna put the Pinewood Derby car up here. Okay. Oh, whoops. That. Yeah, thanks. All right, here we go. Okay. So we got a racetrack, got Pinewood Derby car up here. It's gonna roll down to the bottom, where here's like the finish line. Right. Ooh, it's gonna build up some linear speed for sure. Right? Also the wheels rotating, and say you did like a physics approach with this. I bet one good approach would be conservation of energy. Maybe not the only way to think about it, but probably right. So sum of energy initial equals sum of energy final. Now that's if it's a closed system. If you did consider that there was maybe some friction acting along the way, maybe the friction on the wheels, say between the wheels and the axles, right? I might say minus work done by friction, right? Maybe make it an open system type, right? Okay. Let's put this together. Right. So this is a framework, but what about the specific bits that would go into these places? Okay. So sum of energy initial. Here, give this an angle, call this length L, call this H, which you guys know is equal to this L in terms of this L, sorry, this H in terms of this L data is equal to what times what? L sine theta, right? You guys know that? I mean, that's one of the first things we ever did in this class, right? So trigonometry. Okay. So what type of energy does the car have at the top? Is it potential energy? Okay, so MGH. Okay. Okay. Now, by the time it gets to the bottom, see, some of energy has gone into friction. So we're going to subtract that out of the system. Okay. Could that be the frictional force times the length of the track? friction force times length of the track, which, by the way, that friction force, you guys know isn't friction force equal to coefficient of friction times the normal force? And isn't the normal force mg cosine theta? Right, so you could substitute that all in here if you wanted to, but just keep the sort of big picture. Right? By the time the car gets to the bottom, what type of energy does it have? What are you guys thinking? Kinetic, right? Kinetic, is that like 1/2 mv squared? But the 1/2 mv squared is just the translational kinetic. That's how, like if you point a radar gun at it, how fast it's moving, that's what that V is. But you know what? I bet those wheels rotating, some of the energy actually goes into making the wheels rotate. And this is part of the point that he was making in that video that I showed you. He said one of the techniques, one of the big techniques you can use to win the Pinewood Derby race is to actually lift one of the wheels off the track. So there's only 3 wheels instead of 4. Now you might think that would affect the friction, except it sort of zeroes out because now there's a tiny bit more friction on 3 wheels instead of a tiny bit less friction on 4 wheels. So that didn't really affect it a whole lot, right? But what it does affect is the bit that I haven't written over here, which is plus, isn't 1/2 I omega squared like kinetic energy, but in terms of rotation? Now this is for a wheel, and there could be like either 3 or 4 wheels. How do you do it? Let's say you put all 4 wheels on the bottom. I would do 4 times 1/2 I omega squared, where this I is the rotational inertia of a wheel. So that could be like 1/2 mr squared for could feed into that. If you have the mass and the radius of a single wheel. If you have all 4 of them in contact, then you do that. Right? Now, if you lift one of the wheels, like bend one of the axles so that one of the wheels does not rotate, then now this 4 changes to a 3, which means that there's more energy to go into this term, which means that the car is going to be going faster at the bottom and also get there sooner. Okay? And so that's one way you can what's Pinewood Derby is. Okay? So that's a big picture analysis of this. We've got some rotational motion. We got a conservation of energy. Review going on. Okay. Right, but you guys got these puzzles. So, we did all of these yesterday, right? Did all those? So go to the next ones. Right, number 90, topsoil. 10. Oh, let's see right here. 10 bags of topsoil, each weighing 175 newtons. Okay, so one thing right off the bat, just for that first line, you can see is we'll do 10 times 175. That'd be 1750 newtons is the entire stack, right? 1750 newtons of weight. Okay. Placed on this sheet of wood, they told you how long it is. Their stack, and they told you what this is. So they told you exactly the location of these things. Okay. We got 2 people lifting the wood, each on one end. So we got one guy over here lifting and one guy over here lifting, right? So we got these 2 guys lifting. Okay. Now, guys, which would be the easier end to lift? The left side or the right side? Definitely the left side, right? Isn't it true? The fact that the bags are closer to the right side, like more of the weight distributes over here, right? And you can figure that out exactly using torque. Actually, first the slide this reminds me a lot of this one. Does that remind you a lot? Let me zoom out again. Okay, zoom out here. Okay. Does that look a lot like that? Do you guys think? Right? Okay. And if they said ignore the weight of the wood, so it's even a simpler than this, because whereas the mg beam, you can just ignore that, right? It just simplifies to that, doesn't it? Right? So, what exactly question did they ask? How much force does each person exert? Right? So there's somebody on the left lifting and somebody on the right lifting. And yeah, this is what you guys said. You guys said the guy on the right lifting is going to feel more weight. Right? There's greater force from the right. Right? The guy on the left gets an easier job. Right? But how do you figure this out exactly? Well, I'm thinking of system of equations to answer this. Right? One is that the sum of the forces has to zero out. So the 2 lifting forces has to account for all the bags of topsoil. But the other thing is it has to do with like where the topsoil is, which is an idea of torque, right? Like radial arm crossed with the force, right? And I gave you guys an example here for this apple. So we'll do something really similar for this topsoil. Actually, you know what I should do? Here. I'm gonna leave this up on the screen. Okay. And I'll give you guys one more hint, and then you guys can solve it. I'll solve it off screen, and then it's kind of like we did yesterday, and then see if you guys get what I got. Okay. One other hint I'll give you guys is that, oh, whoops, that's not even the right. I'm sorry. Where'd it go? I lost it. There it is. Do this up here. Here's what we care about. Okay. You can actually solve the whole thing with just the torque equation. Okay, so just the torque equation. Okay. So again, what you guys are solving is even simpler than what I'm showing up here, but you can use that as a model. So I'll solve it. You guys solve it. Okay. See if you guys get what I get. All right, so I've got an answer. We figured this out. We figured it out. All right, so give you guys one more time. All right, so sounds like Stephen got it, right? So, right, so back to topsoil, right? Okay. So you can use this as a model, but again, it's even simpler because you can ignore the beam here or ignore the wood. Okay, here's what I did this out. Okay, so looking at the wood from the side, the full length of the wood was 2.43 meters from end to end, right? And we put all that topsoil right here at the 1.93 meter mark from the left, okay? And there were 10 bags that weighed 175 newtons each for a total of 1750 newtons. So that's your setup, right? Isn't that your free body diagram? Right, just like that. Okay? Force from the left, force from the right. Now, one thing you could say is that these two forces up have to balance with this force down. I say that like this. The sum of the forces in the y direction has to be equal to 0. That's what that line says right there, right? Force left upwards plus force right upwards minus 1750 newtons weight has to 0 out. Okay, that's one of your equations. Okay, that's one of the two equations in the system. The other equation is a torque equation. Now, for torque, you guys just took a couple of days to do a whole torque lab. You have to pick a pivot point. Now, I like one of 2 points as the pivot point, one of these endpoints. And the reason I like one of these endpoints is because that's going to zero out the torque caused by one of the forces, therefore allowing you to very quickly solve for the other force. Right? I picked this point right here. I said, let's pick this point as the pivot point, as the pivot, right? Treat this kind of like a door hinge. So that's your door hinge right there. Is it true that the force acting at that point doesn't cause any torque? Right? So this torque zeroes out. The topsoil is causing a clockwise torque relative to this pivot point, and the person lifting on the right side is causing an opposing counterclockwise torque. Right? And those two torques have to balance out, don't they? Right? Is that true? So here's the setup. This radial arm crossed with this force, R crossed F, minus this radial arm crossed with this force, and I'm subtracting because we've got clockwise versus counterclockwise. Right? Has to zero out, or you can set plus and you would just get a negative force. So however you do it, right? The torque also has to zero out. That's your two conditions for equilibrium. The sum of the forces is 0. The sum of the torque is equal to 0. But do you guys see that there's only one unknown here? Can you guys do the algebra for this? Right? Take this, add it over, divide by the 2.43 meters. Right? You're going to get 1390 newtons. That's how you get 1390 newtons. Then what you can do is go back to your first equation, plug in 1390 newtons, right there and solve for the lug force, which is equal to this, 360 newtons, right? I mean, that's one way to solve it, not the only way. Alternatively, you could have picked a different pivot point. This would have been the second easiest pivot point to pick right here. Solve for F left first, you would have got 360 newtons, right? You could pick any points in the pivot point and done like a fancy system of equations. You might have to do like a substitution and blah, blah, blah. Right? So there are harder ways to solve this too. Okay. Is it up there a minute? All right. You guys think you figured that out? Okay. Torque goes to 0. You guys are finishing writing that down, digesting that. Okay. Could this be kind of like here? I'll change the story that leaves the picture looking similar. Okay. What if this actually was a door? This is the width of a door. This actually is the hinge. We're looking down from above, like a bird's eye point of view. What if we're looking at that door right there from a bird's eye point of view? Right. And here's the hinge. Right. And here's the handle. Okay. And maybe I'm trying to open that door. So I'm pushing in from the inside of this classroom and I'm trying to open the door. But there's somebody on the outside who's trying to hold us in. It's like pushing us in. Okay? And they're applying the force not quite at the handle, but about right here. Okay? When they have to push harder than I'm pushing, right, to keep the door closed, and those numbers could play out exactly the same. Right? That makes sense. All right, you guys ready for the next one? All right, number 103. All right, zoom in here. Analyze and conclude. A banner is suspended from a horizontal pivoted pole as shown in this figure. All right, so this isn't the best print, but there's like a pivot point right here. Right. So this pole could usually like pivot, right? This pole could usually pivot. Okay. The pole is so many meters long. They gave 2.1 meters long and weighs 175 newtons. Right? Ooh, the fact that they gave you the weight of a pole, isn't that sort of like I gave you a weight of a beam? Right? And now you could say, well, isn't the weight like distributed over the length of it? Which is true, but in terms of a torque equation, is it okay to treat the weight of the beam acting exactly the middle of the beam? Yeah, at its own center mass. So you can go ahead and do that. Right. All right, what else we got? The banner weighs 105 newtons. Right, so the banner has a pretty good weight right here. And it's at the far end, 1.8 meters. Or no, sorry, that's not the far end. Right, but it's pretty close to. Right. So we got 1.05 meters to the center of mass. We got 1.80 meters to the banner, and 2.10 meters is the full length of the pole. And you care about the full length because at the end of the full length, right now, this is the part that printed the worst. Okay, there's a cable at 25 degrees to the horizontal that zips on up that way. Okay, you guys see that cable? Okay, so here's the pole. That's the pole right there. Okay. Here's your banner. Okay. Hanging right here. Okay. So the question is, what is the tension in that cable? Okay. So it's a little bit more complicated than what we did. There's going to be an extra trigonometry step. Okay. I'll solve it off screen. You guys solve it. See if you guys can get that. Okay. Actually, you know, but I'll give you guys a hint. This cable, from the point of view of the pole, isn't this like pulling? So there's like a force here, right, that runs exactly along like the cable, right? A tension force, right? And that tension force, well, it's pulling up and to the left. Can you split that into components and say, oh, up and to the left? That's kind of up and kind of to the left. You can split that into components, right? Say, that's kind of up and kind of to the left at the same time. Okay. And you guys know that this angle is 25 degrees. That means that this angle is also 25 degrees, right? So if this whole thing has some tension, isn't this the tension times what, sine or cosine of 25 degrees? What's opposite of 25 degrees? If you go from hypotenuse to opposite, is that a sine or cosine relationship? Yeah, sine, right? Yeah, we've done like hundreds of those in this class, right? Right? If you want to go from hypotenuse to opposite, yeah, that's a sine relationship. I think it's tension times sine of 25 degrees, right? Right? Now the cosine component just pushes it into the wall and the wall pushes back. But you can solve this but without ever getting into that fight, right? So there you go. That get you guys started. All right, how about now? Anybody got by now? Yeah. So give you guys a little bit better looking picture there, right? Give you guys some more hints. Right? So if this tension is pulling up into the left, isn't like pushing it into the wall. So there's this expert component. Actually, these two have to balance each other out. That's not to scale, but you guys get the idea. Okay. And also there is also the pivot point, a vertical force F sub y, but you don't even have to know that. You can actually solve this whole thing with just the torque equation. Right? The sum of the torque goes to 0. Okay? So yeah, there are other equations too. The sum of the forces are equal to 0 along each axis, but you can solve the whole thing with just this. Okay? Do you guys think that this right here looks like a really opportune pivot point? Right. For a few reasons. One, I mean, it's literally pivoting on that point, but also these forces would cause 0 torque about that point itself. The weight of the beam, weight of the pole, is causing a clockwise torque. The weight of the banner is also causing a clockwise torque. And the tension, which is pulling at this weird angle, well, the cosine of 25 degrees component doesn't add any torque to it. It's like pushing in. But the sine component of the tension causes a clockwise torque, or sorry, a counterclockwise torque. You got clockwise, clockwise, counterclockwise. And aren't those the three torques that have to sum to 0? Right? Can you guys make an equation out of that? R cross F, R cross F, R cross this F, T sine 25 degrees. T is tension, right? Okay. Should 0 up. Here, give you guys a little more time. I want somebody to get this. Somebody's gonna get this. Yeah, Jacob got it. 420 newtons. There you go. All right, so this looks like this. Here's this R crossed with this F, clockwise. This R crossed with this F, clockwise. Okay, so this was going counterclockwise. I went ahead and just threw in a negative sign. If you left it positive, you just get a negative answer. Okay, but got the full radial size, full length of the pole, times T sine 25 degrees. Okay, okay. So okay, do a couple of steps with you guys here. So if you add up all this, what's 1.05 times 175 plus 1.8 times 105? Okay. That's going to give you 372.75 Newton meters is equal to, and then 2.1 times sine of 25 degrees. This together is this value, and that's times the tension. So 0.8875 times the tension. And this T is like the full tension, right? The full tension off on the angle because I took care of this trigonometry. Okay? So then divide both sides by that number, 372.75 divided by that. Yeah, you get the tension is equal to 420 newtons. Okay? So if the rope could handle like 500 newtons before it breaks, then you're good to go. Look at that. Elephant. Hey, it's right there in 4 lines. Point, 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 point. Just like that. Okay. Is that right? Number 7. You use a 25 centimeter long wrench. Oh, look at this picture right here. 25 centimeter long wrench to remove the lug nuts on a car wheel, as shown in this illustration. You pull with the force. Oh, hey, they gave you scientific notation. Guys, what's the easier way to say this number right here? 200. 200. Yeah, that's 200 newtons. 2.0 times 10 to the 2. That's 200 newtons. Now, they probably wrote it this way because that's specifically 2 digits that are significant. Versus if you wrote out the number 200, it's like, well, which zeros are significant? First one would be not the second one. Right? See, right? Oh, and also you pull out this angle that's 30 degrees to the perpendicular line. Ooh, so you're not even getting the full torque that you could be getting. Right? So how much torque are you getting? So I'll solve it off screen. You guys solve it. Ooh, there's a little trick in this one too. Just realized. All right, who figured it out? Who's got it? Anybody? Torque equals R cross F, right? Okay. Here, you guys need to see a picture of a wrench. And this is, oh, wait, how much?
2,500 liters.
Ooh, okay, all right, so I think it's where the trick kicks in. Right, so, hey guys, what, it's not 2,500 or 25, either Newton centimeters or Newton meters. If you got some version of like 25 or 2,500,
Oh,
I think it's one little trick. They threw in a little curveball.
wow. Okay, yep.
Yeah, so, okay.
25.
Huh?
Yeah, 25 Newton meters.
All right. Yeah, so Steve, we're getting either 4330 Newton centimeters or 43 Newton meters. Okay. So
Yeah, 25.
okay, so you guys remember torque equals R cross F, which is RF sine theta. Now the curveball they gave you is that theta right there is not what fits in the definition. The one they gave you is not the definitional theta. Okay. Guys, if this is 30 degrees, then what is this angle right here? Is that 60 degrees? You guys see that? Okay, that's actually what you care about. Because what if, see where it says 30 degrees? What if that you took that down to 0? What if you went and straightened that out, made that perfectly perpendicular? Okay, wouldn't that go to 0? Which means you would be giving your maximum torque. And now, if you did sine of 0, that would be 0 instead of being no torque. No, that's not right. Okay, you actually care about this angle right here. There's two ways to take care of that. You could bounce off that angle, like the complementary angle. So I did sine of 60 degrees. Alternatively, you could do cosine right here, right? So when you see RF sine theta, be careful because it might actually be RF cosine theta. In this case, it is cosine of this angle. Okay, so a little bit of a curveball. Okay? Then they plug in the numbers. So they told you a 25 centimeter long wrench. Told you to plug in with 2.0 times 10 to the 2 newtons. That's 200 newtons. You guys told me that already. Okay, and then here's the curveball you got to take care of. Okay? So I did sine of 60 degrees. Could have done cosine of 30 degrees. Be the same thing. Okay, I got 4,330 Newton centimeters, or if you convert it to meters, the length of the wrench, that'd be 43 Newton meters. Okay. You guys can do that? Right. So that makes sense, right? Like turning a wrench. Okay. Okay. So suppose you want to maximize the torque acting on a wrench. Okay? If you maximize the pushing force, that could help. If you maximize the radial arm, that could help. Like if you push here, that's probably not very helpful, but here a lot easier to turn this nut. Okay? And the third thing you can do is to make this radial arm and this force as perpendicular to each other as possible. Right? Okay. That all feeds into that equation we just did. Okay. And last one here, number 88. A gymnast performing a routine. Right? Oh, and I got a picture right here. Right. Tell you guys what too, if you're hunting around in your book for this, I actually pulled this out of chapter 9. Your book is a little bit out of order. So okay. She does giant swings on the high bar, holding her body straight. That's this picture right here. Then she lets go, grabs her knees and goes into a tuck position. Ooh, do you think she's spinning really fast here? Okay. You know what this reminds me a lot of? finish reading that. Right. That reminds me a lot of this. Remember that? Right. Remember Paul Hewitt had the weights and stood on the turntable and did like the same thing? Right. So large rotational inertia here, small rotational inertia here, small angular velocity here, maybe spinning around real slow, fast angular velocity here. Right? Angular momentum is conserved. I times omega. Right? But there's something really similar going on here. Right? And then finally, she straightens and lands on her feet. Right? So question A, here. In the second and final parts of the gymnast routine, so from here to here, right? What is the axis that she spins around? Around what axis? Do you think it would be around her own center of mass? Around her own center of mass? Right? So center mass is here, center mass is here. Rank in order from greatest to least the moments of inertia for all three positions. Right? Yeah, let's do this together. Actually, let's do the least one first, because I think the least is the most obvious. Which one is obviously the least amount of rotational inertia? Yeah, least rotational inertia. Yeah, this one right here, right? So that has the smallest I value. That's like kind of like, whoops, zoom out here. That's kind of like this one with the smallest I value. She's like tucked in, her mass is distributed closest to her center of mass. And that's like, where's that table? I have here, right here, right? The closer your mass is in towards your center, the less rotational inertia you have. Therefore, you can have a greater angular velocity. Okay. But what about greatest rotational inertia? Now, at a glance, you might say these two tie because she's extended for both of them. But remember that the axes of rotation are different. So between being on the high bar, swinging around the high bar, like here, the axis of rotation is the high bar. Isn't that true? Versus here, maybe you call it like our own center mass. Right. So which one of those, point A or point C, does she have the greatest rotational inertia? Here, give you guys a hint. Look at these two guys right here. When she's going around the high bar, isn't that kind of like this type setup? And when she lands on her feet, so she's just starting to land on the floor. Her center mass, she's going around it. That's kind of like this, right? So this versus this, right? Do you guys see here? If you compare these two, I know. Okay. Right. So 1/12 mr squared versus 1/3 mr squared. You guys know 1/12 is less than a third, right? Okay. So like 1/3 is like 0.333. 1/12 is like 0.08, something like that. Okay. So isn't this a lot less inertia than this? Right? There's not very much inertia like this. There's a lot more inertia like this. So when she's going around the high bar, there's a lot more inertia. That's actually the most rotational inertia that she has. It's going around the high bar. Okay. Okay. So were you guys able to rank those? Okay. Here, I might write it like call these positions A, B, and C. Okay. And they said what? Greatest to least. So A is the most. When she's going in for the land, that'll be the second most. And when she's in that tuck position in the middle, swinging around, that's like the middle amount. Okay. And then I is rotational inertia. Question C. Rank in order from greatest to least her angular velocities in those three positions. Okay. So I'm thinking she has the most angular velocity in the middle. So from greatest to least, right? So omega B is the greatest. Well, she's stationary when she's going up for the land, so I'll call it the least, right? So let's go IA and then IC, something like that. If you consider that her feet are planted, I guess. Right. Yeah.
It's gonna be like the last quiz on some questions for this and then make sure.
Yeah, I haven't written the quiz yet, but yeah, anything that we cover, yeah, I could pull questions off this. Yeah, I could pull questions from labs. We did some labs already. We're gonna do some labs next week. All right, you guys have a great weekend. See you Monday.